Morning. Hello, everyone, and welcome to this month's session. Today, I'll be looking at thermodynamics and the origin of the universe. So, essentially, thermodynamics are kind of some of the most integral underpinning laws to how our universe works, and so it can kind of give an insight into some real big picture things, even though they look a little bit dry on the surface. So, the plan for today is going to look through the laws, learn about what they are. And then I'm going to ponder the implications of these laws and how this might indicate things about the age of our universe, maybe its cause and resulting effects of it. And then I'm going to see how those implications line up with the observed facts that we see and common theories that we interpret from those facts as well. All right, so what are they? They describe the physical properties and interactions of temperature, energy, and entropy, and work as well. And so essentially temperature is, it's the average of the kinetic energy of molecules. And so we're all made up of atoms, small chemicals, that sort of thing. And they're always just moving inherently in a random way. It's called Brownian motion. And the more of this random motion they have, the more temperature they have. And so something hot burns you because it's just got so much movement, so much energy, and imparts that to you, and your pain receptors feel that. And so these are some of the oldest and best tested and well-established laws in all of science. And given that it relates to, how molecules move and how things happen, it's implicit in chemical reactions and forces and all that sort of stuff. Okay, so let's just get stuck into it. What is the first law of thermodynamics? A lot of people are probably familiar with this one, at least the idea of it. It's also known as the law of conservation of energy. And it's the idea that energy cannot be created or destroyed in an isolated system. So obviously the entire universe is an isolated system in terms of scientific thinking. There's nothing outside of it unless there's a God outside of it, if you believe that. But basically within that system, if there's a change that happens, that the energy is never gone, the matter is never gone. It's always ended up somewhere else, somewhere, even if it's not obvious where that is. And so I've got a little balance here indicating that they're always balanced, that they are always the same. And so in more recent times, the last 100 years or so since Einstein, we've observed a slightly stranger idea that energy and mass are actually different expressions of the same thing. So I know they're the same somehow. And this is explained in his famous E=mc² equation. And so Einstein likes to say that, because when we do nuclear reactions, some of the mass will disappear and a lot of energy is there afterwards. And he didn't like to say that, no, we're not turning mass into energy, we're not converting it. We're just expressing the same thing in different ways. But either way, we can calculate the before and the after, and they're never created or destroyed, they're just shuffled around, they just change, they just look different. But all the matter and all the energy in the universe is always the same. And this law would suggest it has not changed since the beginning. All right, so the second law is a bit more cerebral, I suppose, and this states that the entropy of an isolated system is always increasing. So that's not very useful to you unless you know what entropy is. So what's entropy? Entropy is a thermodynamic quantity representing the unavailability of a system's thermal energy for conversion into mechanical work. So we tend to interpret this as a degree of disorder or randomness in a system. And so if I had two boxes that were separated like this, and I had some hot gas here in the red dots and some cold gas in the blue dots, what happens if I take out this middle divider? Because they're random motion, they're just going to bounce around, they're going to mix, and that system is going to become more disordered as a result. And so this second law is the reason that heat energy is so often produced as a waste product. We're really good at producing heat. So the old incandescent light bulbs, invented by Thomas Edison, whoever, only 4% of the energy you put into those actually comes out as light. Vast majority is heat. That's because heat is the most entropic of energy states, essentially. And so heat commonly comes off as a waste product. That's why we're forever cooling computers. That's why lights are inefficient, all that kind of thing. Heat has a lot of entropy, and so a lot of reactions just naturally gravitate towards heat over time. All right, and then the third law says that the entropy of the system, so that disorder, approaches a constant value as the temperature approaches absolute zero. So absolute zero is minus 273.15 degrees. that's where the random motion of these atoms just stop entirely. So you can't have any less energy than stopped. You can't have any less temperature than no movement energy at all on average. And so as the temperature decreases, essentially these guys are less excited. They kind of bunch up together a bit more. And the third law just states that. And this is basically, it informs us about change of state. So a gas has its particles very spread out, and that's why you can move through it. But if my gas was to condense into water, that's water, it's liquid. Those particles are closer together, but I can still kind of move it around. And if it gets colder again, they get even closer together. They form a solid like ice. And so the third law kind of ties in with those ideas as well. But that is always related to entropy, of course, because there are elements of order and disorder at play there. So that's the three laws, but there's also a Zeroth Law. It's kind of more important, but they kind of decided on it last. So hey, let's just call it zero. So the Zeroth Law is it's pretty much an idea more than something. Well, we observe it, but its key is it's an idea showing that if two systems are in thermal equilibrium with the third system, then they are all in thermal equilibrium with other. So if two things are the same and the third thing is the same as those two, well, hey, the third thing has to be the same as well. So that's just kind of logical. But this little logical loop gives us the reasoning that allows us to define temperature without referring to entropy. So this circle helps us to stop having circular reasoning, essentially. But they made it a Zeroth Law because it kind of underpins the others that sit on it too. All right, so that's a little bit funky and abstract, but there are a few specific ideas that I'd like to talk about a little bit more and focus on for our purposes today. Because these have very specific implications, and they're not intuitive implications if you consider life as we know it to an extent. And so from the first law, the idea that matter cannot be created or destroyed, and same with energy, essentially it means what was the matter and the energy always there? Like, was it always there forever? Was there no beginning to time? Like, if it can't be created, it had to have always been there. And from the second law, the idea that that disorder increases over time. If that energy and that matter has always been there, why do we still observe order today? If it's been running forever, it should have run to maximum disorder by this point, essentially. And so as an extension of that from the third one, if it has always been tending towards disorder forever, why is the universe not in this lifeless state where everything's the same temperature, everything's just spread out and, homogeneous, for lack of a better word? And so from this, we can kind of conclude a few things. Essentially, for life to have begun as we know it, we actually need to consider the idea that perhaps at least one of these reliable laws required to be broken for us to even be here. So let's have a look at why or how those laws had to be broken for us to see what we see today in the universe. So I'm going to kind of go through the different possibilities resulting as each of these considerations from the laws. And so from the first law, okay, we can't create matter or energy. And so that leaves us with two options. Option one is it was always there. So there had to have been, so if it was always there, there must have been some cause that resulted in the current effect where we see structure and order in our universe. Because it should just be complete disorder by now. Something must have caused it to have order in the first place. And that probably can't have been forever ago because there is still some of that order left. And so if matter and energy was always there, it creates this idea of, well, hang on, how did that order come from? Where did that arise? Or the other option is to flip things and go the entire way. Okay, maybe it was created, but that breaks the first law. But how? And so we've kind of got these two opposite ideas, but neither of them sit comfortably in terms of what we see today, but also what we know when we see about this first law, a law that we've never observed to be broken. Right, so let's have a look at the second law. So this roughly states that disorder increases over time. So as I mentioned before, we're not a disordered blob. So disorder is increasing, but there's still plenty of order left. Like I'm still in one piece. We can go about our day, the world's not falling apart, all that kind of stuff. And so intrinsically from this, if it was always there and we still have order, there can't have been a forever in between, or we would have arrived at this full, complete disorder by now. And so therefore, there must have been a starting point to this order to allow not so much time that we are still around, essentially. And so from that leads to additional questions. One is, where did that order come from? How did it just arise spontaneously? So how could this come from a big bang? Matter just exploding, causing a universe, and then the chemicals just bumping into each other on Earth to make a cell, which then evolved and all that sort of stuff. All right, so from the third law, that's the idea that disorder approaches a certain value as temperature moves towards zero. Again, this is just additional evidence that, hey, we haven't reached that max disorder yet. We haven't reached a constant temperature in the universe. So again, there must have been a starting point for this order, and it can't have been too long ago. All right, so let's take these possibilities and then fit them into different theories. And so for simplicity's sake, I'm going to focus on two theories. One's going to be the prevailing scientific theory of the day, which is the Big Bang theory. And I'm going to focus on a biblical theory of this aspect and see how this evidence aligns with each of those. All right, so let's talk about the facts and how we can interpret them within the lens of these theories. So we'll start with the Big Bang. So what are the facts? Matter and energy can't be created or destroyed. We're not complete disorder yet. So within the lens of the Big Bang, how do we interpret this? So we consider that the matter and energy were always there. There cannot have been energy or matter created from nothing, because this is all there is. There can't be any supernatural power or anything to create anything. The matter and energy must have always been there. And so the Big Bang theory states that originally all that matter and energy was in a very small place. It was compacted together. It was very hot, very dense. It was just all there together. Don't know why, I don't know how, it just was. And so at some stage, something caused it to explode. And as that matter exploded, the universe expanded rapidly, and all that matter became the universe, all the planets, all the things cooled down over time. And as they cooled, they kind of coalesced into shapes and things and heavenly bodies. And so obviously a lot of thermodynamics did not exist yet or apply in that event. So they're kind of talking pre-laws of thermodynamics. There was just this stuff together. It was always there. It just exploded, and then things happened. And so what's the causative agent that caused that explosion? That is unknown. The Big Bang theory cannot explain that. They cannot comment on that. I saw a famous quote from a university, I forget which one, but like on their physics department door, we had, if T is greater than zero, talk to us, about physics, we can talk about the Big Bang. For T equals zero or earlier, go see the religion and philosophy department, because we can't comment on that. We can't talk about the causative agent. We can only comment on what we theorize with that we've seen afterwards in that expansion after that initial bang event. So from this, what do we think about the origin of order? Like, why are we still not in pieces? And so the reason for that is the result of these fundamental forces created by this new universe. And so today we have things that kind of hold things together, like electromagnetic forces, positives and negatives attract, nuclear forces that hold atoms together, gravity that holds planets in orbits and all that kind of thing. So the origin of these forces is unknown. They just coincidentally happened as a result of the Big Bang, perhaps. And coincidentally, they have the precise values required for life as we know it. So if any of these operated differently, we also couldn't exist. So we've talked about the idea that we live on a Goldilocks planet. It's not too close from the sun, it's not too far, perfect temperature. The universe existing is a giant Goldilocks, because all of these forces allow matter and form to exist. So I've got an article here which I've linked to, and the article is called "Why is a Neutron Heavier Than a Proton?" So neutrons and protons, they're tiny little bits that make up atoms, essentially. And neutrons and protons are very, very similar. They're in the middle of the atom, and one has a positive charge and one has a neutral charge, or just doesn't have a charge. The mass is very, very, very similar. They nearly weigh the same, but not quite. So I think the difference is 0.1% from memory. I forget if I've written it. There you go, 0.1%. So a neutron is 0.1% heavier than the other one. And so this article talks about, well, what if it was the other way around? What if that 0.1% bigger was the other atom, the other subparticle, rather than the other one? And he says disaster. So under these circumstances, isolated protons would turn into neutrons rather than the other way around. Some protons would be saved by attaching to neutrons. But if this was true, hydrogen, the simplest chemical element, which does not have a stabilizing neutron, it would just be protons and electrons, and it could not exist. And so if you swapped this tiny difference in mass between those two particles, the most basic element of life could not exist. And hydrogen is used as the fuel for stars. And so stars could not have existed. And stars could not have produced carbon and oxygen and the other larger elements as a result of nuclear fusion. And so without these no protons, there'd be definitely no water, no biology. You couldn't have all these other elements, couldn't be stars, like nothing would really exist or matter or happen just by a swapping of this 0.1% of a tiny little mass in a particle. And so that's just one factor, let alone the forces to hold them together, the gravity that allows us to orbit things and hold planets together. If any of those factors and the strengths of those forces were different, life as we know it probably couldn't happen. And so the writer concludes with this. Was it just a lucky fluke that the laws of physics turned out this way? Or does it suggest something more profound? Is it a fluke that all these 0.1% line up exactly as we need? Or does it suggest a brilliant balance implied by a designer? So this is not a religious article. This is from a scientific page, and it's kind of blew my mind to see that they were considering these things. All right, so we've talked about the Big Bang, how that might relate to these ideas. So an alternative theory that I'm presenting is the Genesis narrative in the Bible. So we have the same facts. Matter and energy cannot be created or destroyed, and the universe has not yet run to complete disorder. So how do we interpret this in a biblical framework? So matter and energy cannot be created or destroyed. Well, we just say that God made it. He's supernatural. He can do anything. He spoke. It came. It happened out of nothing. The Big Bang doesn't have a good explanation. It kind of breaks the laws of thermodynamics too. So if you're going to break the laws of thermodynamics, you might as well have an amazing God doing it. So he's all powerful. He exists outside the universe and its laws. He can do what he wants because he created it. He made these things happen. And so the structure and order, where does that come from? Well, it's his intent, his intelligence, his creation, his plan for the things that he wanted to see. It makes sense that we see this fantastic order that all fits perfectly. These laws that allow this universe to hinge and interact in the way it does. And so from this, what's the causative agent? God, rather than some unknown because we don't know. And the origin of order is his plan, his intelligence, his thought. He made it happen, whereas order from a Big Bang perspective is, again, just another statistical fluke, same as evolution would be a statistical fluke. The things just happen to come together in the way because they just did, and we're lucky. But an all-powerful God thinking about it, I believe that's an excellent explanation for these things that we see. And so, yeah, we should consider that. What makes more sense? The fact that matter was always there and underwent this transformative change with no apparent cause, with a very unlikely result being highly structured order that in turn over billions of years gave rise to life, or an all-powerful creator that existed outside the bounds of the universe and these laws, who intentionally created them with his structured intelligence. And so either way, whichever way floats your boat, faith is required. We weren't there. You need to take a step and go, well, based on this evidence, I think this, and we can't prove it with what we have today. Both of these interpretations of those same facts require faith. Right, so that's about it. We looked at the laws of thermodynamics, nice and focused today. We spoke about the implications of these laws and what they mean about the origins of the universe and how things are traveling today. And we looked at the observed facts and how these can be interpreted through the lens of a Big Bang theory or a biblical narrative in Genesis. And I'll just finish with a verse from Genesis 1, right in the beginning. In the beginning, God created the heavens and the earth. Now the earth was formless and empty. Darkness was over the surface of the deep. The Spirit of God was hovering over the waters. God said, "Let there be light," and there was light, matter and energy from his words. And here's the references to finish up. Wikipedia is great for standard science concepts because there's a lot of really anal science guys making sure those pages are right. They're very interested in keeping those correct. So you can read a bit more about that there. And then I've linked to that other article there from Cosmos about why a neutron's heavier than a proton. So thanks for listening today, and I hope to see you all next time.